Okay, so I'll be talking about prime numbers. So before that, I just want to say like so what are natural numbers? Natural numbers are like 1, 2, 3 and so on. So there is a saying that God gave us natural numbers and we created everything else. But for understanding the natural numbers, the prime numbers becomes really important. Hopefully by the end of this lecture, you'll feel that okay, probably that is true. So I'll be talking about prime numbers and I'll say something about fundamental theorem of arithmetic, and then maybe we'll see how many primes are there, and then maybe we'll talk about some conjectures and applications. That's what I will do. So maybe I'll go bit quick. So I've just wrote down some, like till 10. I just wrote down the divisors of the numbers. So probably most of you would know what prime number is, and can you say which are all prime numbers here? 2, 3, 5, 7. That's all right. So actually, let me just write it formally what prime number is. So actually, you're trying to find out all the natural numbers whose divisors are just 1 and itself. So that is what is the prime number, what you're defining it. Yeah. Okay. So what we are saying is, suppose if it is not a prime, can I do something with it? Yeah, of course you can do something with it. What you can do is like fundamental theorem of arithmetic says that you can actually write it as product of prime powers. So for example, if I go back, so there was a 8 I can write it as 2 cube. So it is, and 8 I can write it as 2 cube, and 9 I can write it as 3 square, and 6 I can write it as product of primes. So that is what I meant to say. That is what is fundamental theorem of arithmetic. So most of you might have seen in the school this theorem, but maybe not the proof. Maybe I'll just quickly go through the proof. So if it is a prime, I don't have to prove anything. It is already like it's a thing. If not a prime, then maybe I'll use something called strong induction principle. I'll just state it for you. So what it actually does is, suppose P of m is my statement. So what here I do is I check for some k naught, which is actually called as a base case. Okay. Then I'll assume till n minus 1 this statement is true for this. For suppose this chart piece. Just for the suppose my statement is like 1 plus 2 plus 3 and so on, m, it is equal to m times m plus 1 by 2. So let's say this is my statement. This I call it P of m. Okay. So I'll check whether it is true for the base case. Probably here it will be 1, P of 1. That is true, and similarly I'll assume till n minus 1, and I prove that it is true for P of n. Okay. Then kids, can you switch on the lights? Yeah. So then if that is a true, then this statement will be true for all the natural numbers. That is what is the strong induction is. Okay. So now I want to use the strong induction. So when it is not a prime, what is not a prime, I can always write it as a product of two other numbers. It is no more, it is a composite, so I can always write the product of two numbers. But the nice thing now is this, a and b are both less than n. Okay. Because since they are not, it's not a prime, they are always greater than 1 and less than n. So now I use the strong induction hypothesis. Like I can use a strong induction principle and say, okay, I assume that a and b are no more, like a and b I can write as a product of primes. Therefore, n also is a product of primes. Yeah, then by induction like it will be true. That's all. Okay. So now question is, are the primes infinite? So okay, what I try to do is, suppose I take only 2 primes, 2 and 3. This is very easy to see their primes. Can I produce more primes? Is what question here is. So clearly the 2 plus 3, like plus 1, it is actually 7, it's another prime. So you can actually understand why I am doing it. I am actually using the fundamental theorem of arithmetic to do it. See, now I have, like, you give me 2 primes, I am multiplying it, I am taking plus 1. Clearly 2 and 3 can't divide this 2 times 3 plus 1. But fundamental theorem of arithmetic says that it has to be product of primes. So I can write it as a product of primes. So the new primes getting generated here. That is one way I understand. So here since I have 7, I try with 2, 3 and 7 plus 1. This is the nice way of getting the different frames, 43. So you can see once I go on. So this is like 2, 3, 4, 7, 9. So actually factorizing this is becoming hard, right? So this way is good to get the primes, but somehow some things are getting harder. So probably we'll see the bit easier way, that is called sieve of arithmesis. So where you do is like, what we do is like, you list all the numbers 2 to n. Okay, then you take first 2. So you strike out all the numbers greater than 2 which are multiple of 2. See, finding a factorization of a number is difficult, but dividing some number is multiple of some number is not as easy comparatively. So the next thing is, so next the 3 is not 3 will not be marked out, right? So so next move on to 3. 3 will be a prime because it is not marked out. But now you mark out all the multiples of 3, okay, which are bigger than 3. And this process will continue. And when you reach the number and it is not marked out, then that will be prime. Okay, just so for suppose I am writing it till 100. So I have taken a 2. I marked out all the even numbers, and then go to 3. 3 will remain as it is, and now mark out all the multiples of 3. That way you can actually decide these are the only ones which will not be marked out. Okay. And E. Cerinthus, yeah, he is a Greek mathematician. Okay. Now question is, so suppose if we proceed this way, do we get the infinitely many primes? Is the question. So answer is yes. So but we give a proof by contradiction, and probably you might have understood how the proof goes. So let's suppose there are only finitely many primes. So now what I should do, the way I was trying to produce the primes before. So I'll use the same method. So I'll take a product of all these primes and plus 1. So I know these are the primes and none of this will divide this. But now I go back to fundamental theorem of arithmetic, which says that this has to have prime divisors, and that can't be those. Okay, so they have to be different from this one. So which is the clearly contradiction that there are only finitely many primes. So he is actually Euclid, and this proof is due to him. The idea is due to him. And actually, the question is, so what this is fine if I take all natural numbers, but suppose if I take a particular kind of natural numbers, suppose say 4k plus 1, where like for suppose it is like 5 and 9, 13, this kind of arithmetic progression. So does this arithmetic progression also has infinitely many primes? Does it contain infinitely many primes? Yeah, actually the answer is true, and it's not just about this arithmetic progression, it is for any arithmetic progression it contains infinitely many primes. It is proved by Dirichlet, maybe, yeah. And actually even one can prove using similar way as this. Okay. So what is the biggest prime known till date? Okay, I actually thought of listing it, but I don't want to write a book, so that I didn't list. I just produced a small way. So this actually is a largest prime known, and this contains this like way too many digits. Okay, that's a thing. And actually there are some books just containing the largest prime known till that date. Like I think something came in 2017 or something, but a book from Japanese company which contains just the digits of the largest prime known till date, something like that. Okay, so now we have seen that given any number I can actually write it as product of primes, right? So now if I take a primes and just add them, will I be able to still get all the natural numbers is the question. So suppose first forget the odd numbers will come back later, but let's check whether, if I take 2 prime numbers, so there are only one even prime, right? So the rest are odd primes. So let's take considerably, if I take 2 odd primes and add them, it has to be even number. So maybe let's check if I can generate the all even numbers is the question. So let's see this. 3 I can write it as sum of 2 primes. 8 I can write it as sum of 3 primes. 10 I can write it as sum of 2 primes. 14 yes. 16 yes. 18, 28 of course we can write. So the thing is, the Goldbach is conjectured that any even number can be written as sum of 2 primes. So in 1972 this is mentioned in a letter to Euler. Okay, so this is a conjecture that any even numbers greater than 2 can be expressed as term of 2 primes always. And the weaker version of this, that is every odd number greater than 5 can be expressed as sum of 3 primes, and this was proved by this actually proved by Helfgott in 2013. Yeah. So now probably you should be convinced that okay, the prime numbers are good enough to get a whole natural numbers. But of course there are some conjectural evidences only, not this is still not proved. Yeah. With these conjectures you should be convinced. And maybe like just one, I'll just give one application and I'll close it. So is factorization hard? Of course it is hard. So as you can probably see, like till some smaller numbers you probably able to factorize very easily. But when it goes to larger numbers, it's really hard. Using this factorization is hard. Actually, this is primes is used in cryptography. One is RSA and encryption, another one is the public and private key. So what you do is like if you take two large primes and multiply them, factorizing them into two different primes will become tough. Like that is hard. Using that, they use this public and private keys. Yeah. Thank you for attention.